On June 18, 1972, a saturated hillside above Poshan Road in Hong Kong collapsed, sending thousands of tons of mud and debris into a 12-story apartment building. 67 people were buried alive in an instant. This wasn't a natural disaster in a remote wilderness. It was a catastrophic failure in the heart of a modern city. The victims were families, sleeping in homes they believed were safe. The slope that failed was engineered, designed to be stable, and yet it gave way with terrifying speed. How can a city built on mountains protect its people from the very ground beneath their feet? Welcome to Strong Foundation Engineering. In our last video, we explored how physics-informed neural networks, or PINs, can fuse physical laws with sparse data to create living models. That was theory. Today we're looking at a system that has been doing this at city scale, with real lives at stake for nearly 5 decades. Welcome to Hong Kong, one of the most slope-dense urban environments on Earth. Here, skyscrapers don't just sit on flat ground. They cling to the sides of steep, rain-soaked mountains. For millions, living next to a massive engineered slope isn't a rare sight. It's their daily reality. This makes geotechnical engineering not just a profession, but a matter of public survival. The system wasn't born from foresight, but from tragedy. After the 1972 Poshan Road disaster and another series of fatal landslides in 1976, the Hong Kong government knew something had to change. So in 1977, the Geotechnical Engineering Office, or GEO, was established. Their first major act was creating the world's first territory-wide early warning system for landslides. Think about that. This wasn't an academic project. It was an emergency public safety measure built on the painful lessons of documented failures and lost lives. The goal was simple and brutal: never again. The system had to predict the unpredictable, turning the chaos of a rainstorm into a clear, actionable warning. This system didn't just appear fully formed. It has been painstakingly refined for nearly 50 years. It started in the late 70s with a simple model based on rainfall duration and intensity. By the mid-80s, it evolved into a rainfall threshold model. Then, as more data became available, it became a sophisticated rainfall landslide density model. This is the definition of iterative engineering. It's like a doctor who has treated the same patient for 50 years. At first, they rely on basic symptoms. Over time, they learn the patient's unique history, run more advanced tests, and can predict problems with incredible accuracy. Each generation of the GEO system got smarter, not because of a single breakthrough, but because of decades of continuous data collection, analysis of failures, and incremental improvements. And that brings us to today, the 5th generation platform. This isn't just an update, it's a leap forward, integrating artificial intelligence and big data. The system's core is a machine learning model trained on 380 historical rainfall events that caused documented landslides between 1996 and 2023. Think of it like this. The AI has studied nearly 400 case studies of when mountains fail. It has learned to recognize the subtle, complex signature of a storm that is truly dangerous, distinguishing it from thousands of other heavy rainfalls that cause no problems. It's no longer just about how much rain falls, but about the specific patterns of intensity, duration, and geographic distribution that precede a failure. So what does this AI upgrade actually mean in practice? The results are stunning. The new system increased the accuracy in predicting the number of landslides to more than 90%. The previous system, which was already world-class, was at nearly 70%. That 20-point gain isn't just a number for a research paper. It translates directly into saving lives. It means more precise warnings, allowing authorities to evacuate the right areas at the right time. It also means fewer false alarms, which prevents warning fatigue and ensures that when an alert is issued, people take it seriously. This is where AI stops being a buzzword and becomes a critical tool for civil engineering. What makes this AI so powerful and credible to engineers is that it isn't just a generic pattern matcher. It's a geotechnical specialist. The models are slope-specific, tailored to Hong Kong's unique geology. It integrates not just rainfall data, but also crucial engineering parameters like man-made slope geometry, soil type, and historical maintenance records. It's like the difference between a generic weather app telling you heavy rain expected and a structural engineer telling you that specific beam in your house is under stress because of the load pattern. The AI understands the physical system it's monitoring. It knows the difference between a granite slope and a volcanic tuff slope, and it knows how each one behaves under pressure. This is the critical fusion of data science and domain-specific engineering knowledge. But even with 90% accuracy, the system is not a magic bullet, and the geoengineers are honest about its limitations. An AI trained on historical data is, by definition, prepared for the past. Climate change threatens to bring rainfall events with intensities and durations never seen before, potentially pushing the system outside its training envelope. This is why the human engineering layer is irreplaceable. The AI provides a probability, a powerful data-driven warning, but the final decision to issue a citywide alert still rests with experienced geotechnical engineers. The system also has a continuous learning capability, allowing it to improve itself as new data comes in, and it's all supported by robust infrastructure, a network of IoT sensors and cloud computing, making it a resilient utility, not just a fragile app. It is a tool to empower expert judgment, not replace it. The Hong Kong Geo system is a monumental achievement in civil engineering. It's a living system that fuses decades of hard-won experience with cutting-edge AI to protect millions of people. It tells us with incredible accuracy when a slope is at risk. But to truly understand why a slope fails, to look inside the soil mass and see the physics of how rising water pressure reduces effective stress and overcomes the soil's angle of internal friction, we need to go back to first principles. In our next video, we'll perform a forensic geotechnical analysis of a real landslide, peeling back the layers to understand the mechanics of failure from the inside out. Don't miss it. Subscribe and hit the bell to be notified, and check out our playlist for more deep dives into foundation engineering.